In this chapter, we're going to take a look at how we can apply derivatives to some different concepts than we did in chapter 2. In this first section of chapter 3, we're going to be taking a look at something called extrema. So, a lot of what this chapter is going to be concerned with is the way curves behave and the way we can sketch them and their properties. So to kind of start off that idea, we're going to do a little introduction to the way we sketch curves. So let's suppose we wanted to graph the parabola y equals x squared. Maybe back when you first learned about parabolas in your algebra days, that your teacher might have given you a little table to fill in or to make with your x and y values. You would have plotted those points and your teacher would have shown you connect those dots in a manner that makes the shape which we call a parabola. But that's what we call a well-behaved function. We know it's the same shape every time when we have a quadratic function. So the techniques we've used in algebra for graphing functions don't always demonstrate the subtle behaviors of curves, especially what I guess I'll call weird curves, or not your normal kind of graphs. So it's not really possible to know what the graph of a function looks like with certainty only using algebra, again, unless it's one of the ones we happen to know, for example, parabolas. So here's the question that's going to kind of drive us to understanding why curves act the way they do, and that is this: what keeps parabolas from wiggling between points? In other words, why do we always draw the shape of a parabola the way we're used to? Why don't we ever, in between points, kind of make it wiggle back and forth? So that's going to kind of drive some of this chapter in terms of what we're going to look at. So what could we use to maybe describe more accurately what graphs look like? Well, the only thing we've really studied so far in calculus is the idea or concept of a derivative. So we're going to be using derivatives to describe more accurately what graphs and curves look like. So you'll notice something just to kind of start off our analysis of these parabolas. On the left side of our parabola, we know the slopes are decreasing. In other words, the derivative is negative. The slopes are going down, and just remember, slope means derivative. So our slopes are decreasing, or in other words, the derivative is negative. So we know a function is decreasing if the first derivative is negative. Why is that? Well, if something's decreasing, it has negative slope, and that is to say the derivative is negative. Well, the same can be said about increasing parts of functions like the right side of a parabola. If a function is increasing, then the first derivative must be positive. Why is the first derivative positive? Well, the slopes of an increasing function are positive, and again, slope means derivative, so we know the derivative is positive. At the bottom of our parabola, what is the derivative doing? Well, to the left it's decreasing, to the left the derivative is negative, to the right the derivative is positive, so right in the middle, what is it doing at the bottom of our parabola? Well, the derivative's kind of doing nothing. It's neither increasing nor decreasing, or the slopes are neither increasing or decreasing. Okay, so what exactly is extrema? Well, it's exactly what you see at the very top of the slide. All extrema is another way of saying a max or a min of a function. And that's it. We can kind of start taking a look at extrema just with that simple definition. So you'll see we basically have the same graph 3 times. We're looking at the interval from -1 to 2 of this particular graph. And what we want to do is identify any maxes or mins, or in other words, extrema. So what is a max? Well, it's just the highest point that a function achieves, or it's the x value where the point gets to its highest point. So you'll notice the very right side of our function, we have a maximum. That's the highest point of the graph. When I say highest, I'm talking about y values. What about this point at the bottom? Well, that would be the minimum. That is the lowest point in terms of the y-axis that our graph goes. What about the graph in the middle? Well, at that point that used to be a max, now it's not a max. Since it's an open circle, if you guys remember back from previous math classes, that open circle, which is a hole, doesn't exist. So that point is not a maximum anymore. What about the point at the bottom? Well, that's still a solid circle, so we can still call that our minimum. It's the lowest point on the graph, and it does exist, unlike the point that has a hole now. Okay, so what if we kind of switch it up a little bit? What if I fill in that circle again, which again makes it a max? It's the highest point of the graph, and it does exist since we're filling in that circle. But now at the very bottom, where we used to have a minimum, we have a hole. Since that point doesn't exist, we know our graph has no minimum. That leads us to this theorem called the extreme value theorem. What the extreme value theorem says is that if you have a function that's continuous from A to B, in other words, from one point to another point, then that function f must have an absolute max and an absolute minimum. And you can kind of see that in the example up here. An example of the extreme value theorem is this first example we went over. It's a continuous function on a closed interval. These brackets mean we're dealing with a closed interval. In other words, we're including the point A and B in our graph. So this first example shows the extreme value theorem. We have a continuous graph on a closed interval. In other words, we're including the endpoints. So we have to have one max, at least one absolute max, and one absolute min. The next two examples kind of show the opposite of the extreme value theorem, or the extreme value theorem doesn't apply. In the second example, we don't have a closed interval. We have parentheses, or open holes, at the endpoints. For the last example, we do have a closed interval. -1 and 2 have filled in circles, but it's not a continuous function since there's a hole in the inside of that pink region. So let's take a look at a few more graphs so we can get practice identifying these maxes and mins. But we're going to call them absolute maxes or absolute mins if it's the absolute highest or the absolute lowest point. So this first graph, is it continuous? Yes. Are we on a closed interval? Yes, we have solid dots at A and B, so there has to be at least one absolute maximum, which you can see right there, and one absolute minimum, which you can see right there. That's the absolute highest point of the graph for the max, and that's the absolute lowest part of the graph, which is the min. Okay, let's take a simpler looking graph now with not so many up and down parts, just kind of a little parabola or a piece of a parabola. So, do we have a continuous function? Yes. Are we on a closed interval? Yes, A and B have solid dots. So we have to have at least one absolute maximum and at least one absolute minimum. And you can see right here, the highest point of the graph occurs at the endpoint B. The absolute minimum occurs not at the endpoint, but at the bottom of this graph, so there's our absolute min. The last graph kind of is the simplest graph we can draw just to prove that it doesn't matter how complicated your graph is or how simple your graph is. This extreme value theorem works in all cases. If, again, your function is continuous, which this one is, and we're on a closed interval, which again, A is a solid circle, B is a solid circle, so there has to be at least one absolute max and at least one absolute min. And you can see our absolute max happens at the endpoint B. Our absolute min happens at the endpoint A. So hopefully something you're taking away from this is absolute maxes and mins can occur at an endpoint or somewhere in between. Okay, so hopefully the idea of absolute extrema is a little bit clearer now, because now we're going to throw in one more type of extrema, or maxes or mins, and that is relative extrema. So we need to take a look at relative versus absolute extrema. So first things first, if we're looking at the graph, we have a continuous graph on a closed interval. The endpoints are solid dots, so we know there's at least one absolute maximum, which you can see occurs at the right endpoint over here, and we know there's one absolute minimum, which happens to occur at the left endpoint. It's the absolute highest point, and it's the absolute lowest point. But what is this different kind of extrema called relative extrema? Well, relative extrema are informally defined as hills or valleys. Relative maximums are what we call these little hills, and you can see that in this pink box in the graph. So we can call this a relative max because it's a hill. Relative minimum. Well, informally, we can call those valleys, these little dips in our graph. So we see one also in our graph over here, so we can label that valley also as a relative minimum. So it's nice to know what these relative maxes and mins look like visually. If you want to think of a max as a hill and a valley as a minimum, fantastic. But we need a more solid, well-defined way to show what relative maxes and relative mins are. Before we get to that though, on the AP test, they don't always use the word relative. Sometimes they'll call them local. So sometimes you might see the word local max or local min, but just realize that's the same thing as relative max or relative min. The same can be said for absolute maxes and absolute mins. Sometimes they're referred to as global maxes or global mins. So kind of an extra little piece of information you're going to have to realize, unfortunately, but just some vocabulary that you'll have to keep in mind. Okay, so back to the problem at hand. How do we define what a relative and a relative max and a relative min are with some math so that we're better equipped for showing where these hills and valleys occur? Well, you'll notice something about these hills and valleys. The derivative at the hill is 0. In other words, the slope on this hill is 0. The derivative is equal to 0. And the same can be said for our valley or relative minimum. You'll notice that the slope at that point is 0. It's a horizontal tangent, which means our derivative is equal to 0. So if you ever wanted to find a relative max or a relative min, maybe we would have to figure out where the derivative is equal to 0. And we'll eventually get to that point, but for now we just need to know relative extrema occur where the derivative is equal to 0. There's one other thing though, and that's why there's an or. We'll get to the reason why, not quite yet, but the derivative can also be undefined at a relative max or a relative min. But again, we'll focus on that a little bit later, but at least realize, at least from this graph that's shown here, our derivatives are 0 at relative maxes and relative mins. So we can now hopefully start practicing identifying these extrema, these maxes or mins. So what we want to do for each of the points on the graph is label them as absolute maxes or mins, relative maxes or mins, or maybe they're nothing. So let's start off with point A. Point A is the absolute lowest point on our graph. There's nothing below point A, so we know that's an absolute min. But is it also a hill or a valley? Well, no. So all we're going to call point A is an absolute min. So what about point B? Well, point B we can see right away is a hill, so it's for sure a relative max. But is it also the highest point on our graph? Well, you can see that there are points above B. So all we know about point B is since it's a hill, it is a relative max. What about point C? Well, it's not a hill, it's not a valley, it's not a high point on the graph, and it's not a low point on the graph. So we can say point C is just nothing, it's neither. What about point D? Well, point D is a valley. So we know that it's for sure a relative min, and since point D is not the highest point or the lowest point on the graph, it's just a relative min. Okay, point E. In the last slide, I had mentioned that relative maxes or mins occur at these hills or valleys, and those hills or valleys are very smooth in the way they look. But at point E, I guess you could call it a hill, but it's a very sharp hill. So can we consider that a relative max? The answer is yes. The reason that that is a relative max, I'm going to go ahead and put that up. The reason that's a relative max is because it's a sharp corner. I'll go ahead and write that in. It's a sharp corner. But why does that make that a relative max? Well, in the last slide, you saw the derivative can be equal to 0 at a relative max or min, but in another case, it can also be undefined. And that's what happens at sharp corners. Our derivative at a sharp corner is undefined. So sharp corners can also be relative maxes or relative mins. So once we're equipped with that, you'll notice point F is a sharp corner that looks like a valley. And that's again okay to have a sharp corner. Point F is a relative minimum. So what about point G? Point G, if it was filled in, looks like it's the highest point of our graph. But point G is not filled in. Point G just doesn't exist. It's a hole. So can we have maxes or mins when there is no point? Well, we can't. So point G is just neither. Okay, great. Let's take a look at another example. Point A. Is point A a hill or a valley? Well, no, so it's not relative. Is point A the lowest or the highest point of the graph? Well, no, it's kind of in the middle, so to speak, of the highest and the lowest points. So with that being said, we can just say point A is nothing. It's neither a relative or absolute max or min. What about point B? Well, again, point B is a sharp corner, so we know we can call this a relative max. The derivative is undefined at these hills or valleys or equal to 0. But here's an interesting thing about this point. Is it also the highest point in this graph? Well, yes, there is no point above point B. It's the highest point of this graph. So we can actually call it two things. It is an absolute max, and it's also a relative max, because it's that sharp corner hill, if you want to call it that. Okay, point C. Point C, not a hill, not a valley. It's kind of just a point randomly on our graph, somewhere in between. So that's neither. Point D. Point D, again, can't be anything like we saw before with point G in the other graph. It's a hole. Now, if we filled in that hole, I think we would be okay in calling that an absolute min. It seems like it's the lowest point of that graph. But unfortunately, that point is not filled in, so it has to be neither. Point E. It's not the highest point in the graph, but it is a hill, or the derivative is 0 there. It's not a sharp corner, but it is a hill. So we can say that it's a relative max. Point F, kind of the same thing, except it's a valley. So we're going to call that a relative min. It's not the lowest point on the graph, so it's just a relative min. Point G, it's not a hill or a valley. It's not the highest point in the graph. It's not the lowest point on the graph, so that's just neither. Okay, so that brings us to the point where we can now kind of collect all of these interesting points that we need to know for this class. So we've already seen a couple. We've seen these absolute maxes and absolute mins, but more specifically, we saw the hills and valleys, which we call relative maxes or mins. So there's a couple more I need to point out. We see this sharp corner here, and there's actually a name for these sharp corners, or at least the ones that look like this. Those are called cusp points. And that's just a point where the curve abruptly, very fast, reverses direction. So it's kind of a special kind of sharp corner. But either way, we know at these sharp corners, our derivatives don't exist. There's one other interesting point we haven't really looked at up until this point, and that is this one right here. These kinds of points contain tangent lines, just like our maxes and our mins, our relative maxes and our relative mins. So we can have tangent lines that go through a curve in this manner. But you'll notice though, it's a very special case because it's not a max and it's not a min. It's not a hill and it's not a valley. It's kind of in between something that looked like a hill and something that could have been a valley. So this collection of points, the relative maxes, where we have a derivative of 0, the relative mins, the cusps, the sharp corners, and these different kind of tangent lines, all of those points we call critical points. And it's kind of an appropriate name. They're very critical, they're very important points. Okay, so how do we define what a critical point is? Well, again, we already know that relative maxes and mins, where our derivative f prime of x is equal to 0, that applies to that point, and that point, we know that at least at critical points, our derivative could be 0. And I guess it also applies to our kind of weird kind of tangent line right there. In all 4 of those points, our derivative is 0, and since those are critical points, that's one way to define a critical point. But of course, we still have our cusp, our sharp corner, so to speak. So we also know critical points happen when the derivative is undefined. So very important information to know so we can try to find these critical points. One other note that needs to be made is that these relative maxes or mins only occur at critical points. Maximum and minimum points on the inside of a function will always occur at critical points because that's how they're defined. But keep in mind, critical points are not always maxes or mins, and the example of that is again this weird case up here. Critical points might not always be maxes or mins. So we'll eventually get to the point where we can decipher between the two, but for now you just need to know these little facts about critical points. Okay, so let's practice finding critical points. But now we're not going to have any graphs to just try to identify them. We're going to have to use some math to find the actual x value where we have critical points. So here we have our function g, and we need to find critical points. How do we start by finding critical points? Well, we know the derivative is very important. It's the derivative at critical points is either 0 or undefined. So we definitely need a derivative. At this point in this course, we've practiced taking derivatives a lot, so I might kind of pull back from describing each step in the process of taking a derivative. So hopefully you're okay taking this fairly basic derivative. Okay, so there we have our derivative, and we want to find where is the derivative equal to 0. We'll figure out undefined in a moment, but one step at a time. So let's set our derivative equal to 0. This is a quadratic equation, so we need to try to factor it. But before I try to factor it, I noticed there's a 3 in common here, and I didn't show it there. I'll go ahead and put it back in. I factored out a 3 from each term. Of course, that 3 in the front really doesn't matter. It'll go away since we're equal to 0. So now we just need to factor what's inside the parentheses, set each of those equal to 0, so we get 2 points. X equals 3 and x equals -1. Okay, so looks good. Now we need to check the other case. Is our derivative undefined? Well, a quadratic function is really never undefined. If we have quadratic functions, they are defined for all x values. We can plug in negative numbers, zeros, positive numbers, and we won't get anything that's undefined, or we won't be dividing by 0 or anything like that. So there are no points where our derivative is undefined, which means our final answer for our critical points is just at x equals 3 and at x equals -1. Let's take a look at a little more complicated problem. We have our function h, which is x to the 1/3 power. So luckily the process is still the same. To find critical points, we need to see where the derivative is equal to 0, and we need to see where the derivative is undefined. So let's take a derivative. This is a nice simple one. Don't overthink the process. We'll bring down the power and reduce the power by 1. Unlike chapter 2, or mostly like in chapter 2, we would have left that as our final answer if we'd just been asked to find the derivative. In this chapter, we're going to be solving a lot of equations equal to 0. So starting in this chapter, if you didn't get used to it in the last chapter, we need to always make negative exponents positive exponents. It will make problems infinitely easier if you do it that way. So, is our first way we wrote the derivative acceptable? Of course. But since we need to set our derivative equal to 0, it's going to be a lot easier to solve the problem if we send that negative power down to the bottom of the fraction with the 3. Once you do that, now we can set our equation. Now we can set our derivative equal to 0. And if you're kind of looking at an equation and wondering what x might be equal to, it's because we might not have an answer here. Why don't we have an answer? Well, if you think about this for a moment, the derivative is never equal to 0 since the numerator is always the number 1. And you have to think about a fraction for a moment. Can we divide the number 1 by anything and get 0? Well, that's not possible. It just won't work. There's nothing we can put in the bottom of this fraction so that when we divide 1 by it, we get 0. The other way you can kind of look at this problem is if you take this bottom and cross multiply it, so to speak, with the 0, you'll get 1 equals 0, and of course that's not true. So you can look at this a couple different ways, but ultimately we don't get any answers from setting the derivative equal to 0, and that's okay. Because now we need to check for where the derivative is undefined, and we know something about fractions. We know since our derivative is a fraction, fractions are always undefined when the denominator is equal to 0. So in this case, we need to see where is the derivative undefined. Well, again, since we have a fraction for our derivative, we just need to set the denominator, what's in the bottom, equal to 0. And of course, that's a very easy thing to solve. We don't really need any steps. If x is 0, well, then the entire thing is 0, so x is equal to 0. So we have one critical point at x equals 0. Okay, in these last couple examples, they're going to kind of be like the last slide in that we're not going to just cheat by looking at a graph. We don't have a graph to look at, and we need to figure out where we have extrema of this particular graph from -5 to 10. And when it just says the word extrema, that's talking about absolute extrema or relative. So we're looking possibly for both, or one or the other, but we have to go through the whole analysis of it to figure out where we might have absolute extrema or relative extrema. So how are we going to attempt this problem? Well, you have to remember something back from the visual pictures we saw earlier. Absolute extrema can happen at either endpoint or somewhere in between, but we know relative extrema happen at the hills or valleys somewhere in a particular range. Or I'm sorry, not a range, but a domain, an interval, or if you want to call it a window. So let's go ahead and start by finding those critical points, because we know relative maxes or mins occur at those critical points. So we got to first find those critical points, which means we need to take a derivative. So the derivative of our function is x squared minus 5x minus 24. So you got to keep in mind critical points occur at either the derivative being 0 or the derivative being undefined. So let's first set our derivative equal to 0, which is pretty simple. We can factor that quadratic, and then we see we get two critical points, -3 and +8. We need to check for when the derivative is undefined, but it's just a quadratic equation, so f prime of x is never undefined, so I won't bother putting that down unless you want to make note of that. Okay, so the best way to do these problems is to kind of keep them organized, and we're going to make a little table. We're going to take our critical points and take our two endpoints and figure out what the y values are at those endpoints and critical points. The reason we want to find the y values at those points is to see what is the highest point we have and what is the lowest point we have. So it's really just a matter of plugging in the numbers that we have now. We're going to take a look at the left endpoint, the two critical points, and our right endpoint. So without going through the details of showing the numbers being plugged in, all we're doing is taking, in this case, the -5 and plugging it into our original function, not the derivative, our original function. If you do that, you'll get 15.833. We can test our two critical points next. If you take -3 and plug it into your critical point, into your original function, you'll get the y value of 40.5. Next, we'll test the other critical point, which happens at 8. We'll get -181.3. And if we take our right endpoint and plug it in, 10, we'll get -156.7. So it's pretty easy to identify our absolute max and our absolute min now. We can see that the highest point of this graph occurs at -3. We can see the lowest point in this graph occurs at +8. So those are our our absolute max and our absolute min. Our absolute max is again at -3, 40.5, and our absolute min is at 8, -181.3. But there's something else you got to keep in mind here. Since our absolute max happened at a critical point, we know critical points are what we call, or what could be called, relative maxes or relative mins. So since our absolute max occurs at a critical point, we also know it's also a relative max. Since our other critical point happened to be our absolute min, we know that that is also a relative min. I'm going to go ahead and graph this function just so we can cheat in a sense and double check and see if that makes sense. If you graph the function from above, from -5, graph it from -5 to +10 in that window, you'll notice the absolute max happens at our hill, which is also a relative max. You'll notice that our absolute minimum occurs also at a value which is a relative minimum. So the math checked out. I just put this graph here so we can check it visually. Okay, this last example is just like the previous slide, but the purpose in doing this one is to point out one little trick that might end up happening in certain types of problems. But first things first, we're trying to find the extrema of the function from -5 to -2. And again, extrema could be absolute or relative. So we're looking for the absolute and or the relative extrema. So to find those relative extrema or possible relative extrema, we need to find some critical points, which means we need to take a derivative, which is not difficult in this case. To find critical points, we need to set our derivative equal to 0. In this case, it is not factorable. If you tried to factor it, it wouldn't quite work out. So if you use your TI-89 to figure out where this equation is equal to 0, you get two different points, -4.07 and 0.737. Again, like the last example, we really don't need to show that we're checking when the derivative is undefined because we just have a simple quadratic equation. There's no fraction in our derivative, so this is always going to be defined. So unless, again, you want to make note of that on the side, we don't have to really show that we're checking where the derivative is undefined. Okay, so let's figure out all the y values of the points we have. We again have the endpoints and our critical points. So what are we going to do? Well, we're going to take our x values and plug them into the function to find the y value. The highest y value is the maximum. The lowest y value is our minimum. So at the left endpoint of -5, when you plug it into your function, we'll get 0. When we plug in the critical point of -4.07, we'll get a y value of 7.035. When you plug in the other critical point of 0.737, you'll get a y value of -48.52. And when you plug in the right endpoint of -2, you'll get -15. So it looks like we have a high y value and a low y value. It looks like the highest y value we have is at 7.035. And it looks like the lowest y value we have is negative 48.52. But that's where the trick in this problem lies. That negative 48.52 doesn't count. Why does that not count? Well, you'll notice something. That x value of 0.737 is not in our window from negative 5 to negative 2. Since it's not in the window, we really don't care about that point. So you've got to be careful. Just because you get x values doesn't necessarily mean you should be concerned with them. The main reason is if they don't lie inside your domain, inside your window, we can completely ignore them. So now we can figure out what the highest point is and what the lowest point is. Our absolute maximum is at 7.035. And our absolute minimum is at negative 15. So there you can see it. Absolute max at the point negative 4.07, 7.035, and our absolute minimum is at negative 2, negative 15. But again, we're being asked to find extrema in this problem, which means if we have it, we need to also identify the relative extrema. And since our absolute maximum happens at a critical point, we know that that's also a relative maximum. Since our absolute minimum happened at an endpoint, it's not a hill or a valley. Again, I'm going to kind of cheat and take a look at this graph from negative 5 to negative 2. And that little window right there where you can see it in red is what we're looking at. And you can see something. I'm going to put dots, close dots at the endpoints. You can see our max happens at a hill, or our absolute max happens at a hill, which makes it also a relative max. Our absolute min just happens at the endpoint, so it's not also a relative min.